All right, good morning. Welcome back. It is Wednesday of 7th week of this weird quarter. Um, so in this video, I'm gonna do the lesson for today, get you some new information, kind of get you going on today's stuff. But do check back throughout today, like sometime in the next, I don't know how many, sometime today, I will post another video about finishing up the quarter. What does the end of this quarter look like for you? Um, yeah, preview to that video. It's going really fast. I don't know if you've had that sense as well, but basically we've got the end through this week, week 7. We've got through next week, week 8. And then for many of you, that's kind of the end. So this is Wednesday morning, so you're looking at 8 days left. There's not a lot of days, by the way. So sometime today I'll do a video about the end of the quarter. And finals and the final day to turn things in, and I'll have some stuff in there for seniors. You're probably getting a lot of information these days, but I'll try to summarize some of it for you also. Yeah, feel free to ask any questions about anything, just like always, and I'll do my best to field them for you. I know things about my class, and if it's stuff that I don't know about, I will help figure out how to get you there as well. Oh, yeah. Cool. So with our 8 days, what are we doing? We are also preview the next one. This class the content is primarily through these daily lessons, weekly quizzes, the stuff that you've been doing the whole time. So if you've been sticking with the class and kind of like doing all the things, great. That is exactly what to do. If for whatever reason different weeks were struggles, it's exactly the stuff that you already have that you want to keep focusing on. That is going to be your key. Like, that's the broad summary to the whole thing. Yeah. Okay, sorry, I distracted myself again. Okay, but here, so we've got 8 days left. We're gonna just keep doing content, basically. And a lot of you noticed that the gas unit felt short after the stoichiometry unit, which it does every year. That's kind of intentional. I put the heaviest, densest, most confusing thing first, and then all the other stuff after that. So, in the next 8 days, you're gonna see rates of reaction, equilibrium. So today and tomorrow are gonna be concepts. Awesome. Friday I'll teach you some math. So you're gonna be doing some math with equilibrium. We've got a weekend on it, and it's not so bad, really. It's algebra with exponents, and aside from that, you'll be fine. And then next week, I'll get you some solution chemistry, so like stuff dissolved in water, basically, usually water, and then some acid-base reactions, and I think that kind of wraps up everything. And we'll have our next and final quiz Friday, I think the 22nd. So Friday at the end of week 8 will be our final quiz. And it's just going to cover all this stuff starting today. You just did your quiz on gas behaviors yesterday, so yeah, okay, great. That's kind of a summary of upcoming things, and I'll post all the calendars for you like usual. Alright, I'm now 5 minutes into this video, and I haven't started on today's lesson. Great, here we go. Okay, I was thinking if I was going to start another one. So today's topic is this, rates of reactions. And your big question here is, how do you speed up or slow down a reaction? So if you want it to go faster, that did unblur. Okay, how do you... or speed up or slow down? Okay, right. So if you want your reaction to go faster or slower, what are things that you can do kind of to it that will cause it to react faster or slower? Season that. Okay. So examples. One example that is totally real world. Let's say you have a bicycle and you enjoy riding your bicycle in the summer, but you don't want it to get all rusty and crusty and gross. You want to slow down the rusting reaction. So things that you do to keep that bicycle safe, those are all ways to slow down that reaction. Alternately, things you might want to go faster. You're starting a campfire or something like that, and you're cold, you want to get this fire going, so things that you do to get your campfire going, those are all things that you would do to speed up your reaction. Tons of examples like that. I usually start this by asking you how to dissolve sugar in tea, although dissolving is not necessarily a reaction. There's some components that are kind of reaction-like, but it's not, you're not forming something new. It's still sugar and tea. But it still kind of works, actually. So, and it gets you to a lot of the things how to, that we're looking for. How to speed up. And I usually just ask you this general question of dissolving sugar in tea, and you say, stir. And you say, use hot tea instead of cold tea. And what else do you say? You say, what's the other one that always is easy? I'll ask you, do you want to use a sugar cube or granulated sugar? Which one's gonna dissolve faster? And usually, so you drop in a sugar cube and it sinks to the bottom and sits on the bottom, whereas little particles. So what is this? This is a larger piece or a lot of smaller pieces. Which one dissolves faster? Which one reacts faster? This reacts faster. We just got 3 of the 5. At some point along in here, somebody remembers biology and how to speed up reactions in organic, life, actual life things. And in biology, you call those things that speed up processes in biology we call them you might know that word. In chemistry, we're going to take that a little bit broader. So biology is living things. Chemistry is any reaction. So all enzymes are all catalysts. Catalyst is the really big umbrella. Enzyme is one type of catalyst. And catalyst's whole job, so catalyst, here we go. Your definition is going to look strikingly similar to what we have up here. The job of the catalyst is to speed up a reaction. without being used up. So you start with a catalyst and you end with catalyst. The reaction occurs. The catalyst is itself the same at the end as it was at the beginning. I was going to say unchanged, but it's not always true. It sometimes changes in the middle, but then it always changes back. So examples are a little bit tricky to imagine, but things like the catalytic converter in your car, just because you drive your car doesn't mean that you use up your catalytic converter. Like, it will last until it rusts, which is a chemical reaction. But the process of processing your exhaust. See, this is being the best example. Like, you don't know what your catalytic converter does, but it takes all the carbon monoxide, the toxic crap, and is it the carbon monoxide? It takes some toxic part of your exhaust and turns it into something that is not toxic. The point being that the thing itself is not used up. So we often do a reaction that I can totally link for you of how to speed up a reaction. And we use a catalyst as one of the things that we use. And often somebody in the class, after seeing this whole reaction, looks in the Erlenmeyer and they're like, hey, there's still like stuff in the bottom. What's that stuff? That stuff is the catalyst that we added, and it's still there. It's ready to go again. We could just add more stuff. You know, like in the reaction that we do, there is a limiting reactant. Once the limiting reactant is gone, the reaction stops. Surprise. But the catalyst is still there. We could just add more of that reactant and boom, there's another reaction going equally as fast because we still have our catalyst. Catalyst is not used up. Okay. Cool. Those are 4 to 5. The fifth one has to do with gases. So if it's gases reacting, so what are examples of gases reacting? For example, your Bunsen burner in lab, that natural gas is liquid, but the part that you actually, like, at the point that it's burning the gas layer on top. So it's actually a gas reaction in your Bunsen burner. It's a gas reaction in your stove also. You know, you pump your natural gas. If you have a gas stove, that's a gas. Surprise. You know this if you've tried to turn it on and it goes tss, but you don't actually get a fire started. You're releasing gas. Don't do that. It's still flammable. It's just now in the air you're breathing. Okay, so it is a gas, and it reacts with oxygen. It's a combustion reaction. Once it gets that spark going. So sometimes you need a little kick to kind of get your reaction started. We'll get into that really soon, actually, but not today. So like your gas stove, you turn the gas on, and it goes click, 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 and it's trying to get the reaction started. Once it's going, those are gases reacting to cause the fire in your stove, a combustion reaction. So if it's a gas reaction, there are some ways to speed up gases that you can't do with other things, including you can compress a gas. You cannot compress a solid. Try squishing a rock, it doesn't work. But you can squish your bag of potato chips, you know, like you can like decrease the volume of a pocket of gas. So things that you can do to speed up a gas reaction, you can decrease the volume. And think about, these are actually the same thing. Decrease the volume or increase the pressure. And what that means is you've got your balloon. Oh, we thought we were done with gases. This is really you know, like, we're more or less done with gases. So here's your party balloon or whatever. And when you decrease the volume or increase the pressure, you're squeezing that balloon. And balloons don't have the strongest surfaces, but if you've got a metal container or something like that instead of just a flimsy balloon, you can squish the gas together, get the particles closer to each other. That squishing, that decreasing volume, increases the pressure. So you're making the container smaller and smaller and smaller, making the pressure inside greater. That will also speed up a gas reaction. That does not apply to your stove. You maintain the same volume of your kitchen and pressure of your atmosphere, which is totally fine. You don't need your stove to go any faster than it goes. Those are the 5. So the original question here was how to speed up a reaction, and there you go. That's how to speed up a reaction. The other big thing that you want to know is, why do these work? What is going on at the molecular level, the particle level, that causes these things to speed up a reaction? Why does this work? And in good news, the same answer applies to 4 of these 5. Here's the answer. They increase collisions. So to react, you need the following things. And we'll even make that another heading. So why do these work meta things? Okay, for a reaction to occur, this is not going to blow your mind, but it is important. 2 particles to react with each other, they need to first meet. Without that, they will not react. If they never bump into each other, no reaction. But, okay, so the first thing that you need to react, you need, particles need to collide. They run into each other, they bump into each other, there's a million ways you can say this. They need to touch. They can't react if they don't touch. Okay, so they need to collide, and they need to collide with enough something. Here's your clue. They need to collide with enough of that. What did we say temperature was? Temperature's actually just a measurement of, wait for that to catch up, energy. So I need to collide with enough energy to react. It's not enough to have a mirror bump. I mean, some things can collide with a mirror bump, but some things really need to like ram into each other. Depending on the reaction, each reaction has its own threshold energy. Some things have higher threshold energies, some things have lower threshold energies. That click, click, click of your stove is what that is doing. It is attempting to generate enough threshold energy to start the reaction. Oftentimes, once the reaction is started, it just kind of rolls itself along. Yeah. So you need your particles to mix, actually touch each other, and you need them to touch each other with enough energy to get that reaction to occur. I talked about it a long time ago, but reactions are the electrons of this. Let's go real easy here. So the electrons of A have to get close enough to the protons of B, and vice versa. The electrons of B have to get close enough to the protons of A so that they actually stick to each other. If that did not make sense, don't worry about it. Go with this, they need enough energy to actually react. And what is that energy doing? It's doing this electron-proton attractive dance, right? Electrons are negative, protons are positive. So you need the negative of this to attract the positive of this, and vice versa, the negative of this to attract the positive of this, to actually form a new compound. The last thing you need, they need to bump into each other with enough energy, and they need correct alignment. Now, there's a lot of ways to think about this. We'll do another example here. If this AB plus C forms A plus BC, B and C have to touch. If C touches A, no reaction. C can slam into A, and since C is never going to stick to A anyways, no reaction. But if B and C, that is the alignment that you're looking for. You need the actual, like, sides of the molecule. If you go back to all those tetrahedrons, things have sides. So you need in this example, since B and C want to get together, you need B and C to actually touch to form that reaction. Another macro level example, unlocking a door with a key. If you've ever gone to unlock a door with a key and it's just not working, it might be the wrong key. That might be your issue. You might be aligning, a key with the wrong door. That could, like, prevent your reaction from happening. Or if if you're just standing there with your key and just throw your key at the door, like, there's a really good chance it's not going to unlock the door. The alignment of a lot of reactions gets complex, fascinating. You can take multiple college level classes on how to do alignment, and actually, really, truly, once you get into the real world and you're, like, working as a chemist in virtually any field, from tech to biology to catalysts, is a huge field. I'm not getting totally tangent here, but the correct alignment is a huge part of how to manage and control to get the reactions that you want to get. Yeah. Okay. So we said these are the things that you need in order to react, and how does that apply up here? Off we go. When you stir, you increase collisions. When you add heat, adding heat is adding energy, you increase collisions. And you increase the energy, this idea of you need to collide with enough energy, so you increase collisions and increase energy. Put that one off screen. You increase collisions, increase energy. This whole particle size business, smaller particles react faster because they collide more. And just kind of like to think that one through, your large piece has a bunch of small pieces inside of it. So imagine taking this cube and chopping it into 1,000 little cubes. All of those little cubes are here before you chop it up or, like, make it into a powder. They're all there. The inside particles can't collide with anything outside of that box. They're stuck inside. Those inside particles can't react. only on a big box like this, only the surface particles can react. The inside particles are trapped inside. So to increase collisions, you take that thing, you smash it, you turn it into a powder. Suddenly everything on the inside is now also on the outside. Smaller pieces react faster because all of those little pieces inside the big piece, those can all collide and react. This is also called surface area. So this is how many surfaces here. The powder has more surfaces. So this is higher and more. Just to give you that word also. There's more surfaces once it's powder. Whereas over here, most of those surfaces are trapped inside that box. This is a low surface area. Okay. I'm going to skip that catalyst one because that is something else. But this last one, squishing your gas together, like a strong balloon or like a metal container or something like that, if you're squishing your gases, decrease the volume. Squish it means decrease the volume. When you squish it, you also increase the pressure inside. That is also taking all those little gas particles, taking away the space in between them, and that will also increase collisions. We skip this one. This one's different. This one has to do with the correct alignment. So the catalyst aligns the particles so that they will have the correct alignment to react. So it aligns particles into correct alignment to react. There's probably a shorter way to say that, which is also fine. But you get the idea. The catalyst picks up the two particles. This is what they do. So an example down here of AB and reacting with C, the catalyst would like hold on to AB so that the B part is sticking out into the C's. Some catalysts even go the whole way. Some catalysts pick up a BC and they also pick up a C, and then they smush them together. And then BC are then like aligned and like right next to each other. They will react in that case, and then the catalyst will release the finished products. Catalysts work in a lot of different ways. I'm not going to tangent into all of them right here. We can draw what happens inside your catalytic converter. Ask if you want to see that picture. But I think for now, that should just about do it. I'm going to link you a TED Talk on, I think it's a TED Talk. I'll link you a video on rates of reaction. You're going to do a worksheet that is strikingly similar. The answer to number 1 on your worksheet is kinetics. I'll write that down for you somewhere also. I haven't said that word yet. Kinetics, just like kinetic energy, is all about motion. So this word that we've been writing all over the place, collide, most of these things work because they're increasing collisions. Rates of reactions. Oh, let's just write it here. This is really smart. So the fancy word for rates of reactions is, so same thing, reaction kinetics. Okay. I'm not going to put that on your calendar anymore because you've got that in your notes now. Fancy science word for rates of reactions is reaction kinetics. All right. See you super soon. Enjoy.